Okay, this is 3.1, page 6 of the notes. What we're going to try to do now is to match the graph of a function with the graph of its derivative function. Okay, so we have two functions you have to think about. And this is an important concept. We'll use this concept repeatedly throughout the rest of the course, matching functions. So here we have the basic function. This is the function that we're looking at the tangent lines to. On this side, we have y equals f prime of x. These functions are the graphs that represent the derivatives of these functions. Okay, so the y value here is the numeric derivative value from over here. Okay, so let's just jot that down so we remember. The y values here are equal to the slope of the function in the left column. So these y values are just slopes from the prior function. All right, let's see if we can make sense of this. We'll start with the first function, and we're just trying to match these 4 over to this 4. What I want you to look at is what are the slopes at all along these curves. So the obvious slope, I don't know, I think of this one first. If I just go right to the bottom, I know that that has a horizontal tangent right there. So the slope at that point actually equals 0. So at x equals 0, the slope is 0. So if I was trying to find that on these graphs on the right-hand side, I would be looking for a place where at x equals 0, y equals 0 as well. And actually, every single graph has that feature. So that by itself isn't going to help us do any matching. The next thing I want to look at is what are actual slopes here. Now I don't have a scale in here, so I don't know exactly what the slopes are. But if I just think of the tangent lines here, the slopes in quadrant 3 here, the slopes of these tangent lines that I could draw are always negatives. So these have negative slopes. I keep saying negatives. Negative slopes on this side. And let me just stop right there. If I have a bunch of negative slopes when the x values are negative, what I should expect to see when I'm graphing those values, negative slopes here will be graphed as values below the x-axis here. Now there's no values below the x-axis over here. This one has some below the x-axis, some above, so it can't be that. We need everything to be negative values. There's some negative and some positive, can't be that. But look at this one. All these slope values up here, slopes of the tangent lines, are negative. So that corresponds to this graph right here. And further, if you take a look at this, I'm just going to use this to indicate like the tangent line to that graph. That's a pretty negative slope there, pretty steep negative. And as I move the tangent line further along, as I'm getting closer and closer to the origin, that is getting less and less negative. Okay? So it starts out pretty negative and gets less and less negative as I move toward the origin. And you can see that same thing happening right here. Remember, these are the slope values, so I start very negative, and then my slope values get less and less negative as they get closer and closer to 0. So those two parts match up. Okay? These points down here represent negative slopes on the original function, on f of x. Probably off the page. Okay? These are all my negative slopes approaching 0. Negative slopes on f of x are shown right here. So that's enough to convince me that these are the ones that match. Now I'm going to take a look at the right-hand side, positive values of x, and just to make sure, if I look at the slopes of these tangent lines, what kind of slopes do I have here? These are all positive slopes. So on the graph of my derivatives, I would expect all the values on this right side of the graph to be above the x-axis. And if we look here, they are. They're all above the x-axis. That's what that represents. So I start out with a slope near 0. It's getting more and more positive, more and more positive. Here's my slope near 0. It's getting more and more positive as my x values increase. Okay, so let's look at the next one. Here's the next one, a lot more action in this one. Another place you can look to help you when you're trying to do some matching is to look for horizontal tangents. So actually I can see there's a horizontal tangent there, horizontal tangent there, horizontal tangent there, and because I know what this graph is of, it's a horizontal tangent there and there. This might be like a cosine graph or something. So at all these places, I have a slope of 0. Horizontal lines have slope of 0. Now if I'm graphing those slope values, then on this graph, I would be graphing, the y values would be zeros. So I need to find a graph that has 5 y values that are zeros, 5 zeros. And it's going to be the busiest graph here. There's a 0 here that matches with that horizontal tangent. There's another 0 there that matches the x position with this one. A 0 at the origin, a 0 for this x, and a 0 for that x. 5 zeros, 5 horizontal tangents. These match. Now I'm going to check and make sure that it's going the right way. You may in the future have another worksheet where you have to match things that are more similar than these are. I'm just going to pick a location here. I'm going to pick these values right in here. And my slopes in this area are always positive. Okay, so I would expect the y values on this part of my derivative graph to be always above the x-axis from this value of x to 0. Okay, so just in that range. And here we are. There they are. All those values are above the x-axis. Now, why does it go up and then come back down? Well, let's look at more detail of the slope. So I'm going to start at this point and move up to that point. I start out with a horizontal slope. And if I move this just to always be tangent to this, what's happening to my slopes? They're getting more and more positive until I get to a point like this, and then they start getting smaller and smaller until I approach 0 again. So my slopes start at 0, they get more and more positive until they reach that point there, and then they start getting smaller again until they get to 0. That's what's happening right here. My slope starts at 0, and it gets more and more positive until it reaches its most positive or steepest part, and then the slope starts getting less and less positive until it comes back to 0. Okay, the next one. We have this function that kind of looks like x cubed. I'm going to jot that down. It may not be exactly x cubed, but that's what it looks like. And if I notice on this one, x cubed always has a positive slope. Always has a positive slope. We have one spot in the middle where we have a slope that's 0, horizontal tangent right there. But other than that, it's always positive. So what am I looking for on the derivative graph? I expect all y values to be above the x-axis. All the y values should be positive. And the only other place that that occurs is in this top graph right here. So that's where it's going to go. And I'm going to also look at a little more detail just to convince myself that that's true. If I look from here to here and evaluate what's happening with the slopes, I start out with a relatively steep slope, a large positive number, and then the positive numbers get smaller and smaller and smaller until they become 0. And then I start at 0, and the positive numbers get bigger and bigger and bigger until I'm pretty big there. That's exactly what's happening here. I start with large positive slopes, and those slopes get smaller and smaller and smaller until I reach my horizontal slope of 0, and then they start getting bigger and bigger and bigger again, the slopes. So that's a definite match. Finally, there's only one left, but we can just confirm that it works. I'm going to start here with my horizontal tangents, where I have 3 slopes that are 0. I'm going to look to see that my only graph that's left has 3 zeros, and it does. There's 1, 2, 3, and I'm just going to pick one segment just to make sure that the graph is doing what I expect it to do. So I'm going to look at this area here. I expect these slopes to start at 0, go negative, get far negative, and then start coming back towards 0 in that span of x values. Here's that span of x values right here. I start at 0, I become more and more negative, and then come back towards 0 with the slopes. 0, more and more negative slope, and then head back towards 0. So that matches right here. One other thing I want to point out, just something to look for, that'll help us later and become more evident later. If I look at what type of function these are, let's say that's x squared. The matching derivative function is linear, so that's just x to the first power. Look at this third one. X cubed was what the original function looked like. Its derivative function is in the form of x squared. And then this last one, with that W shape, that's like x to the fourth power, and its derivative function is in the form of some x to the third power. So what's happening when you have a function and you get its derivative? Basically, the power is reduced by 1. Now that applies to polynomials. Certainly that didn't work here for this, what may be a trig function. That also won't work for functions that are not polynomials. But a lot of functions are polynomials, and that knowledge that you reduce the power by 1 could help.